Everyone.
The next session, I'd like to invite Dr. Rabih Hammoud from Qatar, NCCCN. He is a senior medical physicist with over 20 years of experience in radiotherapy and research. And with him, I'd like to invite Dr. Wajeeha Anjum, a young clinical oncologist from Lahore, Pakistan.
Thank you. Good morning, everyone. So I'm gonna invite one of the catalysts, actually, one of the health catalysts in the group that Professor Saif Al introduced. So this is Dr. Gustavo Olivera. He's a seasoned healthcare executive with more than 20 years of experience in integrated cancer care across provider and manufacturing sectors. He specializes in leading multidisciplinary teams, scaling operations, and implementing technology in a complex, regulated environments. He has successfully overseen portfolios exceeding $1 billion, led global teams, and supported organizations from startup through NASDAQ-level growth. Let's welcome Dr. Olivera.
I will talk first. Thank you to Saiful Nadim, the invitation to be able to talk here. And I will talk a little bit about quantum medicine. That is kind of a new approach to understand biology and generate imaging for patients. First, I need to disclose some conflict of interest. And I want to thank to all these people that helped on this presentation. The first thing I want to talk is the scale in medicine. You know, when we look at the evolution of medicine, we can see that we go from be able to look at things on microscope to be able to see smaller and smaller things. If we do that, what we see is, for instance, with the microscope, we start to look at histology, you know, microbiology, and so on, that allow to us to see every time smaller things. And those smaller things allow to us to understand the scale and things that happen at every time smaller, you know, the scales. We get after that, to, for instance, to molecular biology, where we start to understand the DNA and different things, you know, that help to us not only to understand how cells are behaving, how we reproduce, and so on, but also we were able to create target therapies, you know, like what we do with, you know, nowadays with many of the target therapies that are based on genomics and different type of omics. But let's think a little bit. If nowadays, when we have an imaging system, even if we have a marker that is telling to us that perhaps we have chances to have a prostate cancer or something like that, really when we have images, we only have a resolution of 1 millimeter. With a resolution of 1 millimeter, we have millions of cells, yeah? If we have millions of cells, we have a lot of chances to, okay, we are catching the cancer too late because they have a lot of chances to spread. Therefore, it will be nice that we have a technology that allows to us to have a much better resolution of when we are able to see a particular type of cancer, because again, even if we know we may have chances to have a prostate cancer, we are not able to identify where it is. And if we cannot identify where it is, we cannot treat it. Way that you cannot move in any classical way. And even though that sounds crazy, we will see there are many examples in biology where that happens. For instance, we have some process where an electron do a tunneling, crossing a barrier that in principle cannot cross, to interact with another molecule to basically catalyze the process. That will happen when we have, for instance, different type of production in chlorophyll and so on. Then the other part that may happen is, for instance, when we smell. When we smell, people believe before that that was related to vibration of the molecules and so on. But we can see that when we smell, what's happening is there are certain molecules that get inside our nose, and what happens is certain electrons create a tunnel that will go to a particular place that will trigger a signal to our brain that will allow to us to smell a particular thing. Therefore, we have certain processing quantum that we will start to understand that are related to biology. And then there are one in particular that is very strange that is called quantum entanglement. Quantum entanglement, what we have is two particles that they are connected, like if you wish, telepathically. If we know what happened in one particle, the other particle will give us information about what happened on somebody else. And I will show you how we use that for medical imaging. For instance, another concept that we need to understand in the quantum world is what is called coherence. Coherence is if we have certain wave function that is moving and we have the right temperature and the right sequence, we will see that basically we can maintain coherence, and basically we can use that to, for instance, generate imaging that in a way that we cannot generate in a different way. And also we will understand that many times we can have decoherence. Decoherence is if I have some particular temperature or particular thing that breaks the coherence of my system, I will be unable to generate images. I will put an example. This is an example of a molecule
protein, which evolves into a quantum superposition of states. This evolution is sensitive to Earth's magnetic field, leading to different chemical products that trigger a neural signal for navigation.
Let me explain this one more time. What happened here is there are certain molecules that depend the orientation that you have respect to the magnetic field is how much of a particular substance you will produce on your body. For instance, there are a bird, a robin, that basically can guide, as a compass, in a particular direction on the north, depending how they point the noise related to the magnetic field of the Earth. And if you think the magnetic field of the Earth is 1 millitesla, that means, an MR is on the order of 1 Tesla. There are magnetic fields that are on the order of millitesla that can change what happens inside your body. Therefore, if we start to understand these type of things, we will be able to understand many of the processes that are happening in our body. For instance, on this particular case, for a robin, when a blue light is incident on the eyes of the robin, depending on the magnetic field orientation, they know if they are going north or they are going south and so on. Therefore, there are a lot of quantum processes that are happening that allow to you to know, how you are moving. Let's go to see some of the applications that are happening with this type of quantum technology. The first one I will talk is a project that is being developed in Poland, where basically they are looking, is similar to a PET, but instead of looking the positron emission, they look at the formation of positronium. Positronium is a molecule or almost an atom that is created between an electron and a positron. And if we do that, basically we can understand not only what happened on a tumor, but we can understand the behavior of the microenvironment around the tumor. Yeah. Therefore, we can know how much oxygen is around the tumor. And this is a device that is being already produced. And already they have some images even in human. What we are doing now in Quantum Theranostics, we are starting two very radical ways to generate medical imaging. One way we call it Quantum Theranostics, that I will explain what we do. And the other is we are using something called an E-ray tube. As you know, you have right now X-ray tube that produce X-rays. We're generating a tube that produces entangled photons. Entangled photon is a much fancy way to generate images that I will explain a little bit. But let's say when we generate imaging with QTX, what is what we do? we basically, when we radiate a patient with radiotherapy, we can look at the radiation that is produced inside the patient, and we generate an imaging using the annihilation of positrons inside the patient. And if we do that, what we have is basically a way to generate an image that is telling to us not only the structure, meaning lysicity of the patient, but also we can know the microenvironment of the tumor, and we can know if the tumor is changing during treatment. Therefore, for instance, if today you have a patient that is doing immunotherapy, you don't know if the patient, the immunotherapy is working when you finish the treatment or not, until you know if the patient reacts to that treatment or not. This type of imaging will allow you to know while you are treating a patient with radiotherapy, if basically the tumor is changing, and it's not only structure information, you also will have information about spectroscopy. You will know what kind of molecules you have inside the patient, and also you will know the kind of change on the microenvironment of the tumor. Yeah. And what is the resolution that you may have? Because one aspect, a key aspect here is we are using detectors that are not measuring attenuation as you typically measure in a CT or in a PET. We are measuring correlation between entangled quantum photons. And that allows is to have resolution on the order of the microns, hundreds of microns, rather than millimeters. Yeah. Therefore, the other thing that we are, let's say, therefore, what type of imaging we should expect from a system like that? Today, basically, you are unable to have an image in vivo that have a resolution less than a millimeter. With entangled photons, you will be able to see region much smaller, and not only understand, the structure of the tumor, but also you will be able to understand what type of microenvironment, if you have hypoxic regions, if you have regions that are related to a particular production of oxygen and so on. Therefore, not only you have a structural imaging, you will have also imaging related to the biology on the region of the tumor and the microenvironment. And let me show you another thing. For instance, but also we are generating what is called an E-ray tube. What is an E-ray tube? An E-ray tube is like similar to an X-ray tube, but it's generating two photons that are entangled. Yeah, these photons that are entangled, one go inside the patient, and the other go to a detector. The photon that never touch the patient is the one that is generating the imaging of the patient. And again, this sounds crazy. A photon that never touch a patient will generate the image of the patient. Therefore, this is an example of how the E-ray tube works. If you have a patient, the photon will cross, through the patient, and essentially you will generate an image with the photon that never touched the patient that is getting information from the entangled photon. And what benefit have that image? Well, you will be able to get a CT with 100 times less dose of what you have today. And not only that, your imaging will have a resolution on the order of 100 microns. That today you have a resolution on the order of 1 millimeter, yeah? And with much less dose. Therefore, what entangled photons and quantum imaging allow you to do is to generate imaging with much less dose, much higher resolution, and not only that, you have only no structural information, but you have information about the spectroscopy of the molecules around the tumor, and you will have information about the type of microenvironment change on the tumor. Therefore, clearly, this is producing a new type of imaging that is combining, if you wish, the information that you have in a CT and the information that you have in a PET, but with 100 times less dose and no need to use a tracer. Therefore, these are imaging of how we look a CT generated with entangled photons. You will have a much bigger resolution than you have today. You will have, again, resolution on the order of 100 microns, and you will have information about spectroscopy of the region that you are treating. Let's say, making long story short, unlike PET, this imaging will generate imaging similar that you have a tracer inside the patient, but without a tracer, yeah? And you will have much more resolution, will be on the order of the 100 microns, and you will be able to have structural and functional information inside the patient, yeah? Let's say, the other thing that is important here is the image is generated with something that is called ghost image. Images are generated by photons that never touch the patient. Therefore, nowadays, when you do a CT, a photon cross through you have a detector that measures the attenuation. In this case, no. The photon that go inside the patient is correlated by entanglement with a photon that is outside. And the photon that is outside is generating the imaging of what's going on inside the patient. Therefore, it's a very different approach to what we do today. And what are the benefits? Again, more resolution, 100 times less dose, and it's not only structural information, but we also have information about the microenvironment of the tumor and the evolution of the microenvironment. Therefore, where we are nowadays, we have imaging on the order of 1 millimeter to 4-5 millimeters. Where we are moving now to imaging that we have on the order of 100 microns and 100 times less dose of what we do today. And again, let's say, why we can do this? The reason why we can do this is because we are able to generate now what is called entangled photons. These entangled photons are photons that allow systems that are not talking today. For instance, like if we have a quantum system, the language to talk between different parts of a quantum system is the entangled photon. And we are generating a source that will produce this entangled photon to generate these images. Therefore, I guess the clear difference that we are producing is imaging will evolve from being, as they are today, like PET tracers, and CT, that is produced with X-ray, to imaging that will be produced by entangled photons, where that will allow you to have much less dose, higher resolution, and information that you cannot get today in any other way. And thank you.
Thank you so much, Dr. Gustavo, for such an innovative and excellent talk. And we can see that this quantum medicine is just not a theoretical one. And with the time, we are moving, it is moving forward from fundamental physics to the meaningful application in the for the cancer care. And with these advances, we can have more precise and personalized treatment. So due to we are lacking the time, so we move forward for the next step. Okay. Seriously.
Yep. Okay, we are starting to design the first prototype of it. Let's say we have a company that we are developing this. We have actually an investor from the Middle East that invests. Sorry, we have an investor from the Middle East that invests on this. We hope to have, and let me mention a quick thing. This type of imaging is not only medical. You can use it for non-destructive testing, for many types of things. For instance, for electronics or for rockets and different things. Therefore, we believe that the first set of imaging that we will start to see with this type of technology will be between 5 to 6 years from now.
Thank you so much. So now